Okay, so what we want to do is we want to talk about finding volumes underneath surfaces using polar coordinates. So far what we've done is we've used we found volumes under surfaces using rectangular coordinate system, but sometimes it's advantageous for us to use polar. Now, let's just recall though. Let's recall a little bit about finding the area of circular sectors. Okay, so let's suppose that we have a sector here. And I will talk about this angle right here. So let's just refer to this angle here as delta theta. Okay, so we start here at an angle and then we rotate up to another angle, and that change in angle is delta theta. Now, if I want to get the area of this circular sector, I need to know, first of all, I know that the area of a circle is pi r squared. But this is not a circle. This is a fraction of the circle. The question is, well, what fraction of the circle is it? Well, I know that in a circle there are 2 pi radians. But this isn't 2 pi radians. This is delta theta radians. So now notice, so this is the fraction of the circle that I'm dealing with, and this is the area of the whole circle. So what I have is, I have that delta theta times r squared, that's over 2. That's the area of this circular sector. Now, let's go a step further, and let's suppose that I don't want the area of the whole sector. I want just this part up here, just this part. Well, let me, for simplicity's sake, let me call this R1. So from here to here is R1, and here's R2. Now, so what I can do is I can get the area of the entire circular sector minus the part I don't need, which is this part. So I'll take delta theta over 2 R1 squared. Now I can maybe do a little algebra here. So I'll factor out a common factor, which is delta theta over 2. And now look what I have. I have R2 squared minus R1 squared. Now this is just begging for more algebra, because notice it's a difference of squares. So let's see what we have. If I do a little algebra with this, I have R2 minus R1, and then this is R2 plus R1. Okay, because that's how we factor a difference of squares. R2 minus R1, let me just call that delta R. Okay, so I'm going to say, okay, this is delta theta, delta R, and then I have what's left is I have R2 plus R1 over 2. Well, notice that is just the average R value. So really, I could say, okay, well, that area is delta theta, delta R, R bar. So the average radius between R1 and R2. So with that in mind, now let's kind of build on that, because what we're trying to do is develop the definition of a double integral in polar coordinates. So let's just suppose that we've got a curve down here, okay? And then we've got another curve. So here is a region, and now let's suppose that above us is some surface, but we're not really concerned about that right now. We've got this curve, which is, maybe g of x, and this curve down here, which is f of x, let's say. And this is all down on the xy axis, or the xy plane. Now, let's suppose that I'm interested in getting the area bounded between these two curves. Well, one of the things I could do is I could divide this into little sectors like we did before. In other words, I could do this. And let me just say I want this right here. Let's look at this. Okay. So let's suppose that I'm interested in getting this area right here. Let's just suppose what I've got here. Now, I could go ahead and make that, and let's suppose that this is like a circular sector. Now notice this is an approximation because I have this part up here which I don't need. Now let's suppose I go a little further and I make those little sectors like I did earlier. We won't make very many, we'll just make a few of them. Okay. So let's suppose I've got this. Okay, so I've got 6 of them here. And what I want to do is I want to use these 6 sectors. I want to get these areas of these things and add them up, and I'm going to use them to approximate that whole area. Well, let's just pick one. Let's pick this one. Okay, and what I'll do is I will fix the theta, and I have the average R right here. Let me just call it R sub I, because this is the ith one of these. And now notice, if I want this area, it's going to be approximately delta theta. Okay, so this times delta R. Okay, and let me just put R sub I, theta sub I, and then R sub I like this. That's going to be approximately what that little area is right there. And if I do that to each one of these, what I have is this. I have a situation where I'm fixing theta. Okay, so I'm going to fix theta, and let's just say I fix all the thetas, and for every theta that I fix, I go through the R's. So what that would look like is I've got R sub k delta R sub k, and then delta theta sub j. So this is me just adding up each one of these. Now let's suppose I go a little further and say, well, I want to do this. I want to take the largest diameter. If I look at all these diameters and I call that and I let the largest one of these go to 0. Remember, I'll let the norm go to 0, and this is what we've done before. If I let the norm go to 0, then this right here, I've got infinitely many of these now. We're going to say that that is this double integral of r dr d theta. So this right here, this will give us the area of that region that we were seeking. So we're playing the same game as we always do. We're in defining integrals, we're just saying, okay, let the norm go to 0. Let the largest partition, the magnitude of the largest partition, go to 0, and we define an integral that way. Now this will give us the area. Let's suppose that we're not wanting the area really, we're wanting the volume under a surface. Okay? So let's suppose we're wanting the volume under a surface. Well, what we're going to do is we're going to have that double integral over that region, and we're going to take the function r theta, r dr, d theta. So in other words, we just put this in. Now if that happens to be just 1, then we're talking about the area. Okay, now let's look at an example that really illustrates why polar coordinates are beneficial. Let's suppose that we want the volume, and we'll just limit this to the first octant under this curve, 25, or this surface. We just want the volume bounded by the xy plane and this surface just in the first quadrant. Now, if we set this up the old way, we're going to have 25 minus x squared minus y squared and I'll just do dx dy. And then I've got to set up my boundaries. Now, if z is 0, what we have is x squared plus y squared equals 25, and that means that x goes from 25 minus y squared. It goes from 0 to 25 minus y squared. So what we would have is 0 to 25 minus y squared. And then y would then go from 0 to 5. And that's what we would integrate. Now the problem comes when we actually try to integrate this, because dig what happens now. We've got 0 to 5, and if I integrate this, I'm going to get 25, I'm integrating with respect to x minus 1/3 x cubed minus xy squared, and I'm going from 0 to the square root of 25 minus y squared. Now that is going to be 0 to 5. Now look what happens. I get 25 times the square root of 25 minus y squared minus 1/3 25 minus y squared to the 3/2 minus 25 minus y squared times y squared. And then this is, I forgot to put the dy over here. This is dy. Now I got to integrate this with respect to y. Now that's intimidating. But if you just take some time to convert it to polar, look what you have. First of all, the 25 minus x squared minus y squared, that's just 25 minus r squared. Because remember that r squared is equal to x squared plus y squared. Okay? Now we have to do the RDR. That's always what we have to do when we're working with polar. And then the d theta. Now the radius goes from 0 to 5. Theta goes from 0 to pi over 2. Because we're just doing the first octant. Now if you do that, if you go through that process, notice how much easier an integral we have. We have, well, let me go ahead and simplify it a little bit before I start integrating. This is 25r minus r cubed dr d theta. I just distributed the r through. And now we have this. We have 0 to pi over 2. And then if I integrate this, I get 25/2 r squared minus 1/4 r to the 4th. And we're going from 0 to 5. So you can see immediately this is a lot less complex. So now we've got 0 to pi over 2. And if I put in a 5 in here, I've got 25 over 2 times 25 minus 1/4 5 to the 4th. Okay. And then there's no need to plug in the 0. Oh, I forgot the d theta. D theta. Okay. So I guess this is 625. 625 over 2 minus 625 over 4. 625 over 4. And you can see that, of course, it's easy after this. Then we would just integrate with respect to theta, and we would be done. And of course, we can combine these, no problem. Of course, that would, let me do this. That's just going to be 625 over 4. And d theta, 0 to pi over 2. And now we would just integrate that, and that would be 625 over 4 theta, and theta goes from 0 to pi over 2. And there we have it. So now we have 625 over 4 times pi over 2, and that would be 625 pi over 8. So that integration is a lot less complex than if we had left it in rectangular form.